Assalamu alaikum and welcome to lecture number 13. In this lecture we'll do some numerical problems on finding the inverse Z transform, and also we'll talk about the LTI system in Z domain. So let's start with the same numerical problem that we have solved in the previous lecture using the scaling in Z domain. So I hope you can recall. So that's the problem which we're going to solve it using the Taylor series expansion. The Taylor series for log of 1 plus x, where absolute of x is less than 1, can be expanded like this. That is log of x plus 1, and this is equal to x minus x to the power 4 by 4 plus x to the power 5 by 5 minus x to the power 6 by 6. Okay, so generalizing it, it can be written as summation n running from 1 up to infinity, and this is equal to minus 1 power n plus 1 x power n. So since it meets the condition that absolute of right, the condition is absolute of x should be less than 1. So for x we have a to the power z. Now we say because a to the power z inverse is less than 1, right, because we know. So or because you can see that z inverse, so z inverse can come this side, so I can write right, that's absolute of it, right? That's the region of convergence. So that means absolute of a should be less than absolute of z, which we have here, right? So that means for our case we have instead of x we have a times z inverse, so that means log of 1 plus a z inverse. This can be expanded as a z inverse, right, minus a square z power minus 2 over 2, right, plus a cube z power minus 3 divided by 2, right, and minus this blah blah blah. So you understand this. So this we can write as summation n running from 1, sorry, I forgot to write n here because it's divided by n, you can see, for 1, so x divided by 1, x squared divided by 2x, so we can write it divided by n. So n running from 1 up to infinity, and we have a z minus 1 whole power n. Okay, so we can also divide by minus 1, right? Okay, I write here minus 1 to to the power n plus 1 divided by n. Or I can also write it like this, n, right, and z power n, or I can write it like z power minus n, right? So that means if you compare it with the standard equation x of z equals to summation, right, and running from 1 up to infinity x of n, right, z power minus n. So that's the standard formula, although this is n running from minus infinity up to infinity, but in case the signal exists from 1 up to infinity, then we can write it like this. So that means if I remove this one, right, this is basically let me write it like this. I can also write it here, right? It doesn't matter whether I write it here or write it. So that means I can also write it as z power minus n. So that means this is your signal, right? This is your signal which you are multiplying with z power minus n. So by comparing with the standard equation, we can tell that x of n is basically a to the power n minus 1 power n plus 1 divided by n, right? So we got this answer. Okay, so I hope this gives you the idea. So you understand that we can find the inverse Z transform using different method, and they result into the same answer. Okay, so here is another example, and in this case we have two ROIs. We have to find the the time domain signal for this x of z. What will be the time domain signal if the ROC, that is absolute of z, is greater than 1, and in case B, when absolute of z is less than 1, right? So you understand this is basically the right-sided sequence, and this one is for the left-sided sequence. So let's try it using the long division method. Okay, so I'll do it for using long division method. You can also do it, make the factors of this one, and then use a partial fraction expansion, and using the inspection method you can also solve it. Okay, so because it's this one, right, so 1 divided by 1 minus 2, so let's use the long division method. So that means 1, right, so we say 1 divided by 1 minus 1.5 z inverse plus 0.5 z to the power minus 2. Okay, so if I multiply it with 1, I hope you understand the division. That's quite straightforward method. So just by 1, so it will give you you multiply this with 1, so you get 1 plus 1.5 sorry, minus 1.5 z inverse and plus 0.5 z inverse. Okay, so when you subtract signs for the this lower will change. So it was previously 1, now it will become minus 1, then it will become plus, and this is also minus. So this cancels with this one, and you get 1.5 z inverse minus 0.5 z power minus 2. Remember that we are doing it for the case when the absolute of the ROC is right-sided, the sequence is right-sided. So we'll expand this one in the powers of z power minus, right? Whereas for the case of left-sided sequence, we expand it in the z such that its powers are positive. Okay, so 1.5 z power minus 1 minus 0.5 z square. Okay, so if I multiply 1 with 1.5 z inverse, so I get this one cancelled. So I hope this you understand. So okay, I do it for the 3 steps, and then you I hope you can understand. We will just generalize it. Okay, so 1.5 z inverse multiplied by 1 will result into minus 1.5 z inverse. Again, 1.5 z inverse multiplied by 1.5 z inverse, it will be 2.25 z power minus 2. Again, if I multiply with this one, so it will result into 0.75 z power minus 3. Now this is plus sign, so when we subtract, you understand, we will change the sign. So this will become minus, so they cancel. This is already minus, it will become plus, and this is already plus, so it will become minus, and we just simply, because they have a different sign, so they'll be subtracted. So 2.25 minus 0.5 will result into 1.75 z power minus 2. Again, this will come as it is, and now we have 1.75 z to the power minus 2. So that means if I multiply 1 with 1.75 z to the power minus 2, I'll get this one. Okay, so multiplying with 1.75, so we get this expression, right? And again, changing the sign, so this will be minus, this is minus again, and this minus, so they will cancel because they both have same sign, right? So it will be so it will have a plus sign, right? Because it's 1.5 multiplied by this will result into minus, because it has a minus sign, so it will become plus. So now it is plus 2.26, and this is 0.75, so it will result into this one. You can verify it, right? Maybe I made some mistake or something like that. Anyway, so this continues like this, right? So that means we can generalize it, and we say x of z equals to 1 over 1. That's the given one, right? And using the long division, we get 1 plus 1.5 z inverse plus 1.75 z power minus 2 plus 1.87 z power minus 3, and so on. So if I write the equation for x of z, so you know that x of z equals to summation, right, and running from minus infinity up to infinity, and we have x of n and z power minus n. So if you compare this one with this equation, so it seems that x of n is 0 for n is less than 0. So that means this is summed from 0, right? 0 up to infinity. So if I expand it, the power series, then we can compare the coefficients, and we can easily find the time domain signal. So that means we have something like x of 0, right, z power 0. Okay, so z power 0 means 1. Okay, then we have plus x of 1 z power minus 1 plus x of 2 z power minus 2 plus x of 3 z power minus 3, and so on, right? So by just comparing coefficient, we can tell that x of 0 equals to 1, x of 1 equals to 1.5, x of 2 equals to 1.75, 1.87, and so on. So we can obtain the time domain signal by using this, right? So I can write it. For the second case, let's we have the ROC absolute of Z less than 1 for, so that's the left-sided sequence. So now we use long division such that x of z would attain positive powers of z. That's condition for the convergence because that's the left-sided sequence. So again doing the same thing, dividing it by, right, so 1 divided by 1 minus 1.5 z inverse plus 0.5 z power minus 2. Okay, now to do this, let's, what should I multiply what with 0.5 z power minus 2 to obtain 1? So first you understand, you compare the coefficient is here 0.5, so if I multiply this with 2 I'll get 1. Okay, then again we have z power minus 2, so what should I get, what should I multiply with this so that I get 1? So that means it has z power minus 2, so if I multiply with z power plus 2, then minus 2 plus 2 will cancel, and because I am also multiplying with 2, so 2 times 0.5 will result into 1, which I need here. Okay, so when I multiply this one with this, so I get 1, then this is also multiplied with this one, so 1.5 z minus 1 multiplied by 2z square. Okay, so 1.5 times 2 will be 3, and this is z power minus 2, and this is z power plus 2, so we get z power plus 1, so we get 3z, right, minus or plus, so we get minus 3z. Okay, then I will multiply this with 1, so 2 multiplied by 1 is 2, so I get 2z square. Okay, so when we subtract, so I'll change the sign, so this is already plus, it will become minus, this is minus, so it will become plus, this is plus, this will become minus, so minus 1 plus 1 stands cancels, and we get 3z minus 2z square. Okay, so again what should I multiply with this one, 0.5 z power minus 2 to obtain 3z? So because it's 0.5, so should I multiply 0.5 with 3? So I'll get 3 5s are 50, right? So also there's decimal points, I'll get 1.5, but I need 3, so that means if I multiply with 6 I'll get 3 here. Okay, because we have 3z, so I need to cancel this 3z. So if I multiply with 6, it will give me 3. Similarly, this is z power minus 2, and I need only z, so that means if I multiply with z power minus 3, then I'll get this one. Okay, so I hope this gives you, it's slightly not confusing, but if you understand that in the previous case in part A, the ROC was z absolute greater than 1, so that means that was right-sided sequence. So for the left-sided sequence, we'll do it in the positive powers of z. Okay, so by multiplying with 6z cube, I get 3z, right? And if I multiply this one, then I get how much? 9. Okay, 9, and this is z power minus 1, and this is z power 3, so 9z square. I'll get 9z square with a negative sign, so that's why negative is here. Again, I'll multiply with 1, so it will be 6z cube, but plus 6z cube. Okay, so on subtracting, this will become minus, so they will cancel. This is minus, so this will become plus, and this is plus, so this will become minus. So 9z square and 2z square, you understand, this has plus sign, this has negative sign, so they will be subtracted. So 9 minus 2 will be 7z square minus 6z cube. Again, now we have 7z square. What should I multiply with this one to get 7z square? So first, if I multiply with 14, you understand 0.5 into 14 will result into 7, and then it has z power minus 2, so because I need z power plus 2, so if I multiply with z power 4, then I'll get this thing. Okay, so similarly we continue with this one and we go on. Okay, so that means x of z equals to 1 over 1 minus 3 by 2 z inverse plus this, and this is equal to 2z square plus 6z cube plus 14z power 4 plus 30 z power 5, and so on. Okay, so again, by comparing with the standard formula, so by comparing we understand that the x of z starts from z power minus 2, so that means from minus infinity it doesn't go up to infinity, in fact it goes up to minus 2. So if I expand it, so it will be something like, okay, I'm expanding it from minus 2, okay, or maybe let's expand it from 0 up to minus infinity. So at 0 we will have okay, let me write x of z here. You understand, in this way we just compare the coefficients to find the inverse z. Okay, so I can write it like x of, for example, 0, right, plus x of minus 1, right. When x of minus 1, z will have, I am replacing minus 1, so minus is already there, so minus and minus plus, so I'll have z. Then I'll have x of 2, x of, in fact, minus 2, so it will be z power 2. Then I have x of 3. Okay, so we have z of 3. Then I have x of 4. So x of 4, not 3, in fact minus 3, right? X of minus 3, x of minus 4. So z of 4, and so on up to minus infinity. Okay, so you can just do it for few terms and then you just put dot dot dot, and that's all. Okay, now if I compare this one with the standard equation, so that means the z square, this is your z square, so this is x of minus 2, so that means x of minus 2 basically equals to 2. Okay, so if I write something like this, I can just write x of n, so x of n equals to how much, 2 for n equals to minus 2, right? Then we have 6 for n equals to minus 3. You see, this is minus x of minus 3, so this is, we have 6 and n equals to minus 3. Then we have 14 for n equals to minus 4, and so on. Okay, so we can, like we expressed in the previous slide, the signal in terms of scaled and shifted impulses. So this, we can say this one is basically shifted by 2 units impulse by scaling factor of 2, so that means I can write it like 2 impulse of n plus 2. Then this one I can write the scaled by factor of 6 and shifted by 3 unit to the left, so that means I can write it 6 plus impulse of n plus 3, and so on. So I hope this gives you idea. That's quite straightforward, that you express it. If this is the right-sided sequence, then you express it in terms of z power minus 1, and if this is a left-sided series, then you can expand it in terms of z powers of the positive powers of z. And how do you know whether it's a left-sided or right-sided? So that is, you get this information from the ROC. So if absolute of z is greater than 1, that means the sequence is right-sided, and if this is less than 1, that means it is the left-sided. Okay, so for left-sided we use the positive powers of z, whereas for the right-sided we use the negative powers of z, right? And once you find few terms, then you can just expand the power series expansion. This method, we call it power series expansion, and you simply compare the coefficients, right? So you find the value, for example, you have 14 here. Okay, Z has coefficient of 14, so if you go Z4, so if you go to Z4, so that means this is basically x of minus 4, so x of minus 4 will have 14 value and so on, right, value equal to 14 and so on. Okay, so as a practice problem, you can do the same problem. We have done it using long division and power series expansion method, so you can do it using the partial fraction expansion. Okay, so that's your homework. Do both of the part 1 where ROC is for the right sided, that is absolute of Z is greater than 1, and part B where we have absolute of Z less than minus 1. So let's come to the next topic, which is LTI systems and Z domain. Okay, so this is the block diagram representation for the LTI system. We have input x of n, we have system response. In this case, because we are talking about the Z domain, so the LTI system has response of h, right, and we have the output y of n. So you understand, in case of the time domain, the LTI system function is basically h of n, the impulse response, and the output for that is the output for that, which is represented by y of n. So we say y of n equals to convolution of the impulse response with the input, or we can say y of n equals to h of n convolve with x of n convolve with h of n. So I hope you understand. In time domain we have convolution. Then if we talk about the frequency domain, so in frequency domain we have the multiplication, right? So if we take Fourier transform of both sides of this equation, then y of n is y of e j omega, and x of n is x of e j omega, h of n is e j omega, and this convolution becomes multiplication. So in frequency domain you simply multiply, right? That's the convolution property. So convolution in time domain results into the multiplication in the frequency domain. And you understand, h of j omega is basically the frequency response of the LTI system, and it is related to the impulse response hn by Fourier transform. So that means if we take the inverse Fourier transform of h of e j omega, we'll get the impulse response, right? That is, when we go from frequency domain to time domain, you just use the inverse Fourier transform, or you use the synthesis equation, okay, or synthesis formula, right? And similarly we have done these things for the Fourier, that we say if the input to the system is e power j omega, that is, if the input is in the form of complex exponential signals, then the output is simply the scale version of the same complex exponential signal, which we call them the eigen function. That is, if the input is complex exponential signal, the output is also some modified version of the complex exponential signal. So we say the input for the complex exponential signal is the eigen function of the LTI system. And similarly, h of j omega, which is the modification factor or change factor, is called the eigenvalue of the LTI system. And we say the frequency response completely characterizes the LTI system in frequency domain, similar to what we say that in time domain impulse response completely characterizes the LTI system. What does characterizes means? That it tells you about the properties, right? You can of the LTI system, just knowing the impulse response, you can just tell whether the given system is stable, whether the given system is causal, whether the given system is memoryless or it is a memory, and so on. So all this information is provided by the impulse response. So similarly, h of j omega also completely characterizes the LTI system. So coming on to the complex Z domain. So in complex Z domain, output is similar to what we have for the frequency domain system, where we say the output is simply product of the frequency response times the input signal. So here also the output is simply product of the input signal times the transfer function h of z is also called transfer function or the system function of the LTI system. The system function h of z is simply the z transform of h of n, similar to what we have, that we say h of j omega is simply the Fourier transform of h of n. So similarly we also say that that's also the same thing, that h of n, if we take the z transform of h of n, then we obtain the system function or the transfer function represented by h of z. So again, like we said, okay, we take complex exponential signal and then we find the output, and then we say that complex exponential signal are basically eigenfunction of the LTI system. So exactly in similar fashion, we can say if you have x of n such that x of n equals to z of n, then the output y of n will be equal to h of z times z of n. So that again similar to what we said for the Fourier case, right? That if the input are complex exponential, then the output are the scaled version of the complex exponential, and we said that this is the eigenfunction. So again it means the for the case of z transform, it's also same that Zn is an eigenfunction of the LTI system, and the system function or the transfer function h of z is basically the eigenvalue of the system, right? So we'll see, just like frequency response, h of z, frequency response and impulse response, h of z also completely characterizes the LTI system in z domain. Like we said that h of z completely characterizes the LTI system. So as an example, for example, we check the causality. So we know that a system in case of time domain, we say h of n completely characterizes the LTI system. So we can check whether the given system is causal or non-causal by just knowing the impulse response, and we say if impulse response is 0 when n is less than 0, then in that case we say the impulse response is right-sided or it is the causal. The system is basically causal. So exactly in the same fashion, we say if the h of z, the system function h of z has an ROC, right, region of convergence, that is exterior of a circle, right? So this condition is for Iir system or infinite impulse response system, right? So for the case of infinite impulse response system, if the ROC is exterior, then the exterior of the circle, then we say the system is causal. Or for the case of the FIR system, that is finite impulse response system, the ROC contains the entire Z plane except the origin and including the point where Z equals to infinity. So similarly, for the case of stability, we say an LTI system is stable if its impulse response is absolutely summable. That means if you sum it from minus infinity up to infinity, right, the absolute value of this, okay, so if it results into some finite value, then we say the system is stable, and if it results into infinite value, then we say the system is not stable. Similarly, for the frequency response, we say if h e j omega converges or exists, then we say the system is basically stable. So for the case of h of z, if the ROC includes the unit circle z equals to unit circle, right? So you understand that unit circle absolute of z equals to 1. If a system is both causal and stable, then all poles have to be inside the unit circle, right? So that's the condition for the system to be causal as well as stable. Then just like we represented the systems by using we represent the LTI system by using a discrete time LTI system by using the difference equation. Okay, so again writing the same equation, I hope you are very well familiar with it. So that's we can represent, that we can represent a LTI system by using linear constant coefficient difference equation, such as this one, where AK and BK are the real constant coefficients. So the Z-transform also provides an elegant approach to deal with systems described by the linear constant coefficient difference equation, which we will see on the next slide. Specifically, we can find it conveniently the system function, right, using the from the linear constant coefficient difference equation. We can easily find the system function, the impulse response, the frequency response, time domain response, etc. And we can also deduce a number of useful properties of the system. Okay, so from the previous slide we continue that we had a different LCCDE. So we take the Z transform on both sides of the equation. So we say, okay, summation k running from 0 up to n, ak z y n minus k, and this one. Okay, so I hope you understand this one. So we just take this Z transform. You understand we have taken ak and bk outside from the Z transform because these are the scaling, and Z transform has the linearity property that you scale the input, the output is also scaled by the same amount. So that means we can take them out. Okay, also using the time shifting property, we say we have done that property also, right? So if we shift the signal in the time domain, in Z domain, it's simply equal to multiplying it by z power the shift factor. So for example, here we are shifting it to the right or left, because k has positive value, so n minus some positive value, right? So I hope you understand, you are shifting it to the right. So that means summation k running from 0 up to n, and we have ak, and y has the Z transform we represented by y of z. So because we are delaying it by a factor of k, so we can say that y of z multiplied by z power minus k, or you can also write it this side. So we say, okay, this equation basically is ak, right, z power minus k y of z, and similarly for this one bk you get the same, and x of n has Z transform x of z, but because it's delayed by a factor of k, so we will multiply with z power minus k. So it will be bk z power minus k x of z, are taking y of z, taking common. Okay, so we are left with summation k running from 0 up to n, ak z power minus k, and similarly taking x of z common here, so we get this thing. So you understand the system response is basically output by input. So y of z divided by x of z is basically h of z. So h of z equals to this. So that means this thing is multiplied this side, right? So if I bring it to this side, it will be divided. So we can say, okay, h of z equals to summation k running from 0 up to m bk z power minus k, and this one, right? So it means that the system function of an LTI system described by linear constant coefficient difference equation is always rational, right? It is rational. Okay, note that the system function in the this equation, okay, which is represented in polynomial form, can also be converted into pole zero form, which we have done previously, or we can also write it in the partial fraction expansion form. So you understand we can write it in different forms. The important thing is that this linear constant coefficient difference equation alone does not provide any information about the ROC of h of z unless we specify some additional constraints such as causality or stability of the system. So we'll quickly finish these. So I hope this expression you understand. Now we take some special cases. Case 1 is when we take ak equals to 0 for all k equals to 1 up to n. So that means we have just k equals to 0, so a naught, and we get something like h of z equals to b of z. That's k equals to 0 up to m, bk, and zk is right. So that's just the scaling thing is left, and all these are removed. Okay, so if I take z power m common, okay, so 1 over z power m common, so I am left with summation k running from 0 up to m, bk z power m minus k. Now this system is called the FIR system, or the finite impulse response system, or filter, because it has finite impulse response, that is h of n equals to b of n for 0 up to, right, for this range 0 up to m. And this is non-recursive system, there is no feedback, right? So as output depends only on the input. The second case will be when bk equals to 0 for all k equals to 1 up to n. So that means you are just left with b naught, and you have a of z, or a of z basically equals to k running from 0 up to n, ak z power minus, and again taking z power minus n common, so we get this expression. Now this system is called the Iir system, or infinite impulse response system, or we can also call it infinite impulse response filter, because it has infinite impulse response, right? The output depends not only on the input, but it also, right, you understand that I think we have talked about the Iir system when we were doing the Fourier, right, discrete time Fourier transform. But anyway, in case of Iir, the output not only depends on input, but it also depends on the previous values of the output, right? The third case will be when bk is not equal and ak is not equal for all k running from 1 up to its limit. Now such a system function is given by the equation of the previous slide, and it is called Iir system, or infinite impulse response system. It's also pole zero system, it may also be called, right? So the output in this case, again you understand, not only depends on input, right? The output not only depend on input, but it also depends on the previous values of the output. So I think I gave you this as a homework. Okay, you are given a system with with the linear constant coefficient differential equation, this one, and you have to find its system function. Okay, so I'll give you the answer and I leave it to you, okay, to solve it. So with this we end the lecture for today. Allah Hafiz.